So relations, functions, we've been talking about all these sorts of things. Well, what's an inverse relation? Everything in mathematics pretty much has an inverse. Addition has subtraction, multiplication has division, and so on. Well, relations and functions, they have inverses as well. Now, what is an inverse relation? Well, it basically returns things back to the start. So how did I put it here? Gets the set of dependent values back to the independent ones. So if we started with A, set over there, and we send it over to Y, and that's Y equals X squared. So there's our function or our relation. If I want to get all those numbers back to those same ones we started with, which I'll now call set C, so we had -2, -1, we're back to where we started from. That would be Y equals plus or minus the square root of X. So it's the inverse relation that would return all of those Y values back to the original X values. The two sets, A and C, end up being equal sets. We've got the same numbers in them. How do you work it out? You simply swap the variables around. So it was Y equals X squared. I wanted to work out what the inverse relationship is, so I just swap the X and Y's around. I make it X equals Y squared, then make Y the subject, and there's the inverse relation. So Y is plus or minus the square root of X. What this means is the domain and range swap around. So the domain of the relation will be the range of the inverse relation, and vice versa. So the other way around. The range of the relation would be the domain of the inverse relation. If we were to look at them both drawn together on the same number plane, they would be reflections in Y equals X. So Y equals X would be like an axis of symmetry for those two pictures. If this was the relation and I wanted to draw the inverse relation, I'll draw in Y equals X, and that's like the mirror. So I've got to reflect everything through this line. Well, that means I can pick important points. And the first one I picked here was this x-intercept. Now to reflect it through, I just draw a line perpendicular to the, axis of symmetry, and then just measure how far across. So the x-intercept became the y-intercept. And then I pick the other ones, there you go. I just moved the other x-intercepts, they became y-intercepts. Then the y-intercept, bing, it became an x-intercept. Other important points, I guess things like the turning points, move them. And any other points you need to draw the graph, as many until you get the idea of the shape. There's some more, and there it is. If you turn your head 45 degrees, oh yeah, look at that. It is a reflection in Y equals X, if you have the two together. So what's an inverse function then? Remember, functions were very specific things. For every X value, there was a maximum of one Y value. So in order to be an inverse function, there has to be a one-to-one relationship. Remember we talked about one-to-one, one-to-many, and so on. So it has to be a one-to-one. That way both the relation and the inverse relation end up being functions. If that's true, we don't call it an inverse relation, we call it an inverse function. How do you test? Well, remember we used a vertical line test to test for a function. You use a horizontal line test to see if it has an inverse. So the graph will satisfy both the vertical and the horizontal. Vertical will tell me it is a function, horizontal will tell me and it will have an inverse function. Of course, if you might not know what the picture looks like, so then it goes back to that idea of swapping the x and the y's around. If we do that, we make it x equals function y, make y the subject, and you end up with something that's unique. There's only one thing it could be, then that's an inverse function. There's the y equals x squared that I talked about before. It's our parabola, of course. And if I draw in a vertical line, it doesn't matter where I put the vertical line, that's fine. It's a function. But if I draw a horizontal line, no good. Cuts it in two places, it won't have an inverse function. Only got the inverse relation. Now, algebraically, if I didn't know what that looked like, I'd go, well, let's swap the variables. X equals y squared, like I just did before. I ended up, you remember, with y equals plus or minus. Plus or minus. It's not unique. There's two things I could have, plus or minus. No good. Not unique, so it doesn't have one. The cubic on the other hand, so here's y equals x cubed, doesn't matter where I put the vertical line, cuts it once. Horizontal line, cuts it once. This one's okay. So it will have an inverse function. Algebraically, if I was to swap it around, x equals y cubed, make y the subject, we get the cube root of x. But when we have cube roots, we don't go plus or minus. It is only the positive cube root of x. So there's one answer, it's unique. So yes, that is the inverse function. Okay, 5F.